All right.
What I've done is I've set up some questions on my own. That way I don't need to do this forward and back thing, which I think is very distracting for everyone. And so I've made up some stories, and we're going to basically do some hypothesis testing about a mean. And I've got a story where you're trying to prove something is different, trying to prove something's bigger, and trying to prove something is less. And although I've made up my questions, I can still use salt because all I need to do is hit the salt button and I can put in whatever information I want, right? So it doesn't really matter too much that way. And plus it gives me a way of talking a little bit more about the story. So this would be an example of statistics being used in quality control. So in a lot of factories, that produce things, they want to make sure that they're producing them to a certain quality, certain weight, certain, all the certain things. In this story, a machine is supposed to fill cereal boxes with 16 ounces of cereal, right? So you can imagine they've got a big funnel and it goes, right? You've seen those machines that like pump out things like that, right? Now you want to make sure that machine's doing its job, right? You might say, well, if it pumps in less than 16 ounces, the company's not going to be too worried about it. But actually, the government has regulations that says if you say there's 16 ounces of anything in a box, there should be 16 ounces, right? You can't just make it 15 ounces and pretend it's 16. And obviously, you don't want it to be putting too much in because isn't that lost money, right? You could get more boxes filled. So there's a reason for why you would want to do quality control. So this is what the machine is meant to be producing, right? This would be the way it would be set up. But from time to time, things change. So you test it. So to test this, because they think that it might have changed, they took a random sample of 20 cereal boxes, which is underneath our like optimum 30, but sometimes you bend the rules to suit the situation. And you do 20 cereal boxes as weighed, and the mean weight comes out as 15.9, and the standard deviation is 2. So that looks like this machine might be underproducing, right? It might be filling them up a little bit less than it should be. But also, couldn't that just be the randomness of it? If you did another 100, it might be 16.1, right? So that doesn't really prove anything on its own. That's why we have to set up the hypothesis test to say, is that unusual? Is the probability of that happening really small? Isn't that what p-value is, right? The probability of it happening, is it really small? And we're wanting to test then, is there enough evidence to prove that the mean amount of cereal produced by the machine is different from 16 ounces? So the key word here is the word different. That is going to be a not equals to story, right? So my null hypothesis will be that the mean that this machine is doing is 16 ounces. And the alternate hypothesis is going to be that the mean is actually not equal to 16. So far, so good. And now we have all the other information is basically going to be put into our salt, right? That's the mean of our sample. That's the standard deviation. And there we are. There's n. And we're going to do a significance of 0.05. So I'm now going to nip over to a salt button. And hopefully it'll work. And we'll see what kind of p-value we get out of it. Now, don't worry about this story because I'm not using this story. I'm just using it for the salt button. And would you agree we're already in the right place? One sample T is where you go with these stories. The sample mean was 15.9. The standard deviation was 2. And the sample size was 20. And we're doing a hypothesis test, and we're saying that it should be 16, and then we're testing to see if it's not equal to that 16. You all comfortable about where the numbers go and how you get them from your story? And then I just generate the results, and there's my null and alternate. The one that I'm really interested in is the p-value. And in this case, the p-value is a ridiculously big number, which is fine. It is what it is. So I'm now going to go back and look at how do we interpret that. Well, once you've found the p-value, you do a test, and the test is the p-value less than the significance level alpha? And it's always less than, no matter whether it's a prove it's bigger, prove it's less, prove it's not the same as. And I think it's pretty obvious that's going to be a no, isn't it? In fact, that's a kind of hell no kind of one. That's a really no one. But we'll go through the process anyway. So 0.825, is it less than 0.05? And the answer is no. And when it's no, don't we have a kind of standard sentence for that, right? And so when it's a no, there's a sentence that is similar to, let me see if I can find the phrase. That way I don't need to try and prejudge it. Right, so the phrase looks something like this. At the alpha equals 0.05, we fail to reject. The null hypothesis. What else? We fail to reject it and conclude that the data is not statistically significant. Are we cool with that sentence? That's the no sentence, isn't it? That's what you say when it's a no. Now, when it's a yes, it's almost the same sentence, but with changes, right? If it was a yes at the 0.05 level, we reject the null hypothesis and conclude that the data is statistically significant. Isn't it basically you rub out the negative parts? And that's what that sentence would look like. And you always get what, a choice of four, don't you? And one of them will be this one. And that's what a no would look like. And then they finish with a second way where you kind of turn it into evidence, or you turn it into a sentence that's more like English. And the one that they typically use for this one is, there is insufficient evidence. At, in this case, the 0.05 level, to conclude that, well, whatever we're trying to prove here, in this case, we're trying to prove that they are different, that the means are different. Now, I want you to pretend that everything here is going to stay the same with one change, just one change. I didn't take a sample of 20, I'm going to take a sample of 200. Now, if you take a sample of 200 and the mean is still 15.9 and the standard deviation is still 2, which I could see easily happening, right? You could get that. Will we come to a different conclusion? Right now, would you agree that p-value is ridiculously big? Right? So if I was just doing this and I was in that factory, I'd be saying to my boss, yep, the machine is fine. You know, keep pumping out the cornflakes. You're not going to get into trouble, right? Things are great. So I'm now going to return to salt. And I'm going to change the sample size to 200. Do you think the p-value is going to get smaller than 0.82, which is what it is right now, stay the same, or get even worse? In other words, get bigger? What do you think should happen if I make this 200 instead of the 20?
Like it'll get smaller.
It should, shouldn't it? Because more data, more accurate should be reflected in the p-value. So here's the 200, 0.82, gotcha. It's now down to 0.48. Would you agree that is still not particularly significant? So I take a whole day's production, 2,000. Ah, you see, it's now statistically significant. Now, that doesn't mean that you, the analogy, do you know how your kids will ask you, in my case, it's my nieces and nephews, don't they keep asking you something till they get the right answer? Right? Can I keep doing this? No. Can I get, can I have an ice cream? No. Can I have an ice cream? No. Right? Isn't that a bit what I've just done there? Haven't I keep trying the experiment till I got the answer I want? Now, the reason why that's not really cheating is that I did make an assumption here that nothing would change, right? That the mean would stay the same and the standard deviation would stay the same. But if you took a sample of 2,000, isn't that a totally new sample, right? So the data would probably change, even if they only change a little bit. The result is that you do tend to get differences eventually in every single situation if you ask enough people, like we did here. And that brings me to a concept that we have to be aware of when you see people doing hypothesis tests. And that is, there is a difference between saying something is statistically significant and its difference is important. What do I mean by that? Can you imagine that you were doing a test to see that, you found the pass rate for students at high school in a certain state is 82%, right? Eventually 82% of the people graduate. Let's say that's our base number, right? And you spend $20 billion improving that success rate. And you take a sample of 50,000 students, right? So your sample is huge. You could prove that you have increased the success rate. But see if it went from 82% to 82.04%, which is an increase. You could detect that difference by having a big enough sample. But the question is that difference actually important? Do you think it was worth spending billions of dollars to get a 0.02% improvement in something, right? So you've got to be aware of, just because someone says it's statistically significant, they might not be telling you anything that's very interesting or important, right? My new drug, my new cancer drug, is statistically significantly better than the old drug. And my new cancer drug costs 20 times as much to buy as the old drug. And my new cancer drug has an extra 0.00002% increase in success rate. Do you see that the extra 0.0002% is not worth the 10 times the money you're going to pay to get it? So just because you're statistically bigger or less than something, shouldn't you also look at how big or less you are? Right? So if the before is 80% and the after is 90%, isn't that a good thing? If the before is 80 and the after is 80 point, a lot of zeros and a 4, that's not such an important thing. And so if someone tells you that, I don't know, drinking milk increases your chance of colon cancer, and they've statistically proven that, making this up, wouldn't you want to know how much the increase in my chances of getting colon cancer is? If they said it's 5% bigger than it used to be, then I might seriously think about not drinking milk. If it's like a 1 in a million extra person dies, would you agree that you're going to die falling downstairs just as often as drinking milk? So it's a risk that you're probably willing to take, right? If you don't want to risk your life, then you shouldn't do anything, shouldn't you? Because, you know, walking out that front door, you're risking your life, right? You could get killed in a car accident. Crazy person could shoot you, right? You could trip over and fall. Right? So, yes, statistically significant things do happen, but are they important? Ask yourself that question as well. Do you ever get anything? I always like picking the medical people because they get this. Has there ever been some reports that have came out and told you that this is better than that? And then when you look into it, yes, it's better, but it's really not that much better worth talking about. Has that happened?
A lot of pharmaceuticals.
All the time.
All the time. So there's this big report saying do this, and then instead of that or whatever it might be, and it's really not a big enough difference to make it worthwhile doing.
Yeah.
Yeah. Is that just because they have to tell you this? I mean, is your life just fluid? The reason I'm saying that is I remember that there used to be one way they used to do CPR, and then they changed it, and they may have changed it twice since when I remember being told how to do it. Are those changes worth it? Are they more successful?
Yes.
So that's a good one, right?
Yes.
Okay.
A lot of our medical statistics that we get, especially when it comes to like CPR and things like that, actually come from China because their population is more dense and they see a lot more like broad range of things. So like how we, like changing the way we do CPR, or like when you're in the field, changing the way you do CPR in specific situations, they get their data from China.
I never knew that.
Yeah, the more you know.
Yeah. And the Chinese aren't lying to you just so they can kill some more Americans.
No, they take really good statistics on like how they figure things out. So we usually take their statistics and formulate away and act like we do it and try it out ourselves. But yeah, they have the population, like the very dense population, to figure that out.
Good. Well, you know me, I don't like governments, but I actually like government data because they tend to be pretty good. So
exactly.
I'm assuming the Chinese government data is pretty good as well. But. Okay, here's my next story. So can you imagine a school? They come and go, don't they? There used to be a time when everybody that was a high school had to do like a standardized math exam and a standardized English exam so they could compare schools and see who's doing well and who's doing badly. I think that died a death, didn't it now? Or is that still going? Anybody throw in and in? Are they still doing standardized math scores with your students, or has COVID basically killed that now?
There's still the SATs and the stuff
right,
like
but right, those are typically voluntary, right? You say I'm going to do my SAT because
my son still had to take the standardized testing for 7th grade last year. So
okay, so it's still going. Okay, so one of the reasons they do standardized testing, I'm sure there are lots of reasons, but one of the ways is it's a way of finding out which schools are doing better than others, right? It's a way of comparing schools, right? So you could do, that's one of the ways they can do it. So in my little story here, a national average for a standardized math test is say 57, right? They have a score, 57 is the average that a normal student anywhere in America is doing. Now, a school district believes that their district is got a higher average than this. So this is a place where they're not doing these tests, but they think our students are good. Let's see if we can prove that they're good. So he tests the hypothesis that their students would get a higher score than 57. They randomly select 200 students, that's good, big number, gave them the standardized math test, and this is what came out. They got 62 on average, and the standard deviation is 15. Right. Now, again, superficially, would you agree that looks like good evidence that it's bigger? So they're on the right track. But remember the one about the 15.9, it was less, but it ended up being totally insignificant statistically. Nothing was going on there. This looks like it might work, right? So how do we prove it? Well, the null hypothesis is that it's still 57. And the alternate for this is that we think that our school district is better than the national average. Now, if this ends up being true, won't this school district maybe get an article in the local newspaper saying, hey, Kitsap County is much better than the national average. See how good we're doing. If this report comes back and it's not statistically significant, or in fact the students did less than 57, isn't there a very good chance that they'll never publish it and never tell you about it? It's very difficult for people to tell you bad things about themselves, right? Bureaucracy doesn't like doing that. But in this story, they might, because it looks like it could be good. And so we're trying to see, is there enough evidence to prove that the mean for this district is bigger than 57? So we got all the numbers. I'm nipping over to salt, and we're going to set up the salt question. Do you think this one's going to have a decent p-value? A really small number, right? That's a decent p-value. What do you think? Do you think 62 is far enough away from 57 to maybe make it?
It's got a very large standard deviation.
So you think that's fighting it as well, isn't it?
Yeah.
That could happen. So I'm going to put in the 62 that we got. Standard deviation of 15. And our sample here was 200. And the mean was 57. And we're trying to see if we can prove that it's bigger than 57, right? So 62, standard 15, 200 people. Is it bigger than 57, right? Everything's set up. When I hit generate results, we're going to go there, right? That's the important place to go looking. And let's see what we get. Whoa.
Oh.
Right. If you were in that school district, would you not be really happy about that p-value? That's very unlikely that you just got lucky and that the 200 students you picked randomly were really clever ones, right? The chance that you happen by luck is like, well, it's almost, yeah, it's almost 1 in a million or 1.5 million. Perfect. Then we would finish by taking that p-value and testing it, although it's pretty obvious what the test is going to look like because it's the same test every time. Is our p-value less than alpha? Is our 0.1, 2, 3, 4, I think it was 5 and a 2, is it less than 0.01? And it is an emphatic yes. And since I am lazy, have I got that guy handy? Yes. Won't I use a version of these two sentences? But it will look like this. At the 0.01 level, we reject the null hypothesis and conclude that the data is statistically significant. Agreed? That's the sentence you would use. And in English, there is sufficient evidence at the 0.01 level to conclude that the mean, whatever it is larger in this case. So you could certainly, quite honestly, couldn't you broadcast that and say, hey guys, Kitsap County is really good education for your kids. In fact, I believe, because I'm in the early stages of looking at houses that I'll be moving to. One of the things you get in some of these sites that you know, if you're looking for a house to buy or rent, won't they tell you the school district number, and they give them a score, at least in the sites I've been, I think it's 1 to 10. And I think 10 is what you want and 1 is what you don't want. I think that's the right way around. I can't remember. Actually, it doesn't matter to me where I retire what that number is, because I'm not going to have any kids going to those schools, so in a way it doesn't matter to me. But it would matter to parents, right? Because you want to make sure your kid's going to a good school. I'm pretty sure that they collect that number based on some kind of standardized information somehow, right? I don't think they just make it up, oh, that school's a 5, call it good. Are we comfortable with the storylines? How you take a story, turn it to salt? I've just got one more of these guys to do. Just so I'm not using up the homework questions, because there's so few of the damn things. If I did them, you know, you wouldn't really get practice on your own. So here's my last one. I believe this is correct because I looked it up. That the average blood pressure of an adult is 124. Does that look about right for a guy? Okay, we'll call it good. It has been stated that meditation will reduce your blood pressure. Maybe it does, maybe it doesn't. So if you had that statement, wouldn't you want to try and see if there's evidence to prove it or disprove it, right? So in my story, to see if there's evidence to prove that this is true, in other words, it will reduce your blood pressure, we did a quick clinical trial, and they got a random sample of 500 people, and they were given instructions on how to meditate. And after 3 months, they had their blood pressure measured, right? So that would be one way to organize it. That's probably the worst version of a clinical trial. Shouldn't I have taken the 500 and split them equally into 2 groups, say 250? And one group, I just told them, you're in this clinical trial, just do what you're doing. And the other group, I'll show them how to meditate, because we wouldn't have a better comparisons, because I'd have a before and after kind of group. But this one works, right? So we got these 500, we showed them how to meditate, and 3 months later, we checked their blood pressure. And lo and behold, the average for this group was now 122, and the standard deviation is 5. And this particular one is no blind. You agree? There's no blind. You know that you're doing meditating, right? And you kind of know they're checking your blood pressure. So if you think meditation will reduce your blood pressure, couldn't it reduce your blood pressure even although I had nothing to do with it? You know, that's the, so I'd be worried about this data in all sorts of ways, which is why I am pretty worried about, you know, those stories that appear in newspaper that tell you this and that's good or bad for you. They're very often designed very badly, so I tend to ignore them. Anyway, in this one, there's the results. It went down. Standard deviation is 5. Is there strong enough evidence to show that meditation will reduce your blood pressure? So the null hypothesis is that it's still going to be on average around 24. The alternate is, will it reduce it? Okay, so time to, oh, what do you think this time? 122 is less than 124. Standard deviation, not big, not small, but maybe enough. 500 people is good. Agreed, big is better. If I did get something significant, I think this would qualify as statistically significant, but not very important, right? Because I'd be worried that the noticed difference was maybe mostly placebo effect plus 2 units isn't going to make a big difference to your life.
Your alpha is very high too.
Yeah, so it's going to clear that hurdle very easily, right? So all in all, that's a bad, it was picked because it was bad, right? But a bad way to do this, right? But of course, if you had a magazine called Meditation Monthly, is it this the kind of thing that you might publish? because you've got an vested interest in making people meditate. Not that they're wrong meditate. Here we go. I didn't do the calculation on this, so I don't know if it's going to make it or not. My gut feeling is I don't think it's going to, but that could be proved wrong. So in this case, the mean of the people was a little bit less. It was 122. Standard deviation was 5, but there was a huge number of people in that sample. So that's helping it, and that's hindering it, right? That's which one's going to win in the one. Now, this number here is the null, which is it's 124, and we're trying to prove that it's less than. So watch this guy over here. Generate results. Wow. What do you think was the main contributor to getting such a small p-value?
Sample size.
Yeah. You start getting into the 500s and plus numbers. If there's even a little bit of a difference, you can very often detect it. But a little bit of difference isn't very important, agreed? So anyway, we got it. So we're using it. And we'll do our test. Is our p-value less than significance? Is 0.1234? I think it was that many, or at least a number that's less than that. And the answer is yes. And I've killed this sentence too many times. I don't think I've got it anymore. Do you know the two sentences we had? Wouldn't this be at the 0.1 level? There's enough evidence to reject the null hypothesis, and therefore statistically significant result. And that in English would become, yes, we have proved that meditating will reduce your blood pressure, but by a very insignificant amount. And most of that could have been caused not by the meditation, but by the placebo effect that might affect the result, right? If you think meditating is going to reduce your blood pressure, it will, a little bit. Probably a little bit would be 2. Now, if you wanted to do a better version of that, 2 groups, right? 2 groups of people, right? One meditating and the other not, right? It wouldn't be a good idea to get 250 people who meditate and 250 people who don't. Because if you picture groups that way, they wouldn't be really similar enough. Would you agree that people who do a lot of meditation probably have a better lifestyle? You know, vegetarian, don't eat a lot of meat, you know, do all sorts of cool things like that. So won't that group necessarily probably have a lower blood pressure anyway, right? So I'm trying to think of how I could get better data out of that. So take 500 people, right? Split them into 2 groups, that's something, right? One lot meditates, the other doesn't. But I'm trying to figure a way of getting the meditation. I've got it. One group gets taught how to meditate. This is me trying to destroy the placebo effect, right? One group gets taught how to meditate, and the second group gets taught a newly made up exercise that you do 5 minutes a day. And it could be anything you like, right? Nose, ear, touch your toes. Nose, ear, touch your toes, right? Whatever it is. Just some useless piece of exercise I don't expect to have any effect, right, on blood pressure. But won't the placebo effect now be balanced? Because both groups think that the thing they're doing is going to make their blood pressure go down. So that would be how I might cope with the placebo effect. Have both groups given something that makes them think it's going to work. Any other suggestions that you could get around that problem?
You could have the control just sit and read a book for the 5 minutes while the others meditating for the 5 minutes to mimic being calm on both ends.
Also, they're doing something that doesn't involve exercise, because mine might accidentally help, whereas reading a book shouldn't. Yeah. So when you are designing an experiment, right, a clinical trial or whatever, you want to try and find the best way to get in the best there, right? I guess that's the bottom line. Right. So let's now just return, to something I want to do here. And that is, if I can set the thing up, is just look at some of the homework questions, and then we'll move on to our last section in hypothesis testing. So, is this one up here? Yes. So, can I make this bigger without losing the writing? That's the question. Okay, I can. Right, Pyramid Lake is in an Indian reservation in Nevada, and they have a reputation of having big cutthroat trout. Your friend tells you that the average length, according to the people in the area, is you get about a 19-inch long trout on average. A surveyor reported that a random sample of 46 fish that were caught had this length. And there is your significance level, and there is your S. Would you agree in this story, you've got all the things you want, right? You've got your sample mean, which is 18.6. You've got your sample size, which is 46. You've got your sample standard deviation is 2.9. Don't you have your null hypothesis is that it's 18, and that your alternate is that it's less than 18? Can't you plug all that into SALT and get your p-value, and off you go? We comfortable? Basically, it's another story. There's your null and alternate significance figure. That's always the same, isn't it? Yeah, they do this weird thing. We did it yesterday on Friday. They don't tell you the p-value is nothing 0.022, right? Don't they just give you an interval of values? And so whatever your p-value is, it's going to fall in some interval, and that's what you pick here. This guy is a left. That's prove something is less than. Isn't this prove something is more than? Isn't this prove something is not equal to? And isn't this don't ever pick it because it's never an answer, I would assume. And then you have two classic sentences to finish. And picking socially conscious stocks is good. Did you know that arsenic occurs naturally in groundwater? That's that thing that people take to, commit suicide, isn't it? Well, I don't think they do it because it's a horrible death. Isn't arsenic poisoning bad for you? Well, all poisons are bad for you, but isn't it a kind of nasty way to go? Yeah. So anyway, you don't want that. Arsenic in groundwater. The mean arsenic level of 8 parts per billion is considered safe for agricultural use. So what's that? 8 molecules of arsenic for every billion molecules that are out there. Okay, nothing is ever zero. Would you agree that's close enough to zero, probably not to cause any injuries, right? So that's fine. And 36 are tested, and they got 6.9, and the standard deviation is this. And does this evidence that this well is less than the safety level, right? In other words, it's okay to drink water out this well or whatever, you're good. And it's off you go and do this basic same question. Right, in this question, they have done something a little bit harder. Have you noticed that the data is very small? And secondly, have you noticed that they haven't told you the mean or standard deviation? And don't you need them to be able to do the hypothesis test? So we've got one more level to do now. We're going to be given data as numbers, and we have to find the mean and standard deviation, which is why they're putting these things there. So I'm going to bring this over. I'm going to hit salt. I'm going to bring this back. And here is salt. So here is salt. I've just hit the thing, right? And here is my data. Now, somewhere along here, I'll be able to get the mean and standard deviation without actually doing it by hand. Okay, it's a while since we've done that, but which one of these headings do you find the mean and standard deviation?
Descriptive statistics.
You would find them there. And if you did that, do you see that the mean is 4.4 and there's your standard deviation, right? And that's good. Now, if I hit inferential statistics, do you see it's already put the numbers in for me? So I didn't know it was going to do that. And I'm kind of pleased that it done that because it means it's actually, you don't need to do the first level, right? It's already there. So the mean is 4.4 and the standard deviation is this horrible decimal. So I'll move that out and I'll kick in here. No, I'll kick in here. There we go. So all I would do is copy the mean, put it in there, copy the standard deviation, maybe round it off if that's what they want. And they want it to 2 decimal places, so I shall do that. Right. So actually, if you just use the sort button, it will go straight to this place you want. And then basically from this point onwards, don't you just do what you did every other question. Here's some data. This is about snow avalanches. If I use the sort button, and then I do inferential statistics, you see it's all set up for me. I just need to prove, is it bigger than or less than whatever the question's asking. Same again. Same again. Oh, one more. And let's do this one since it is the last one in the list. Tree ring dating from archaeological excavation sites is used in conjunction with other evidence to try and figure out how old a site is, right? So you dig up a site and you find evidence that people lived there, and you're trying to figure, well, when was this little village, being used? And you can use tree data. I think if you're using tree ring data, don't you have to have pretty big lumps of wood? If you build your house with a big, it's not a tree branch, what do you call it? A tree stump, you've got enough to see rings. So that's one way you could do it. Here is, based on that and other evidence, a list of different numbers associated with a particular area. And they used potsherds and stone tools and all sorts of other things. And this is roughly when they think that particular area was being inhabited. And if I use the sort button, I'll hit the inferential statistics, and the average is about 1268 AD, and the standard deviation is about 37. And we want to show, assuming the tree ring data on this area followed that is approximately known, does the information indicate the mean population is different from 1284? Okay, so I need to prove that it's different from 1284. And generate results. And would you agree that p-value is not significant? So no, you couldn't, based on that data, you couldn't get any significant result. Do you feel comfortable about means as one population means? The kind of thing we've done, right? Okay, then we are ready to close off a load of windows now to start the last section on, darn it, I've lost my thought process. Our last section on hypothesis testing. which is hypothesis testing for two means. So I'll do a little bit of theory behind that. And then it's going to be very similar to all the other hypothesis tests. Aren't we probably going to use salt to do almost all the number crunching? We just need to get used to where do the numbers come from and how do we use them, that kind of thing. So I think I'm ready. Let's go. So I like to put headings every time we do something, so you just be patient. There's Math 146. We're doing chapter 8, and we're doing testing a hypothesis for two means. It's very, very similar to testing the difference between two proportions. Remember those ones? Right. And they're going to do a little hiccup thing, but I'm still doing it the way I do it, and we'll live with it. So let's have two populations here, two distinct groups of people. And population one is going to be males. And the second group is going to be population two, is females. And I'm just going to make up a story. No basis in reality, just pretending it's true. And I think that the iron level in males is higher on average than the iron level in females. I think that's true. Right? And I want to see if there's evidence to prove that. That's a classic hypothesis test for two means, right? You try to prove one population mean is bigger than the other, one population mean is less than the other, or one population is different from the other, right? The classic bigger than, less than, or not equal to, right? That's the only three kinds that we have. So in my story, the null hypothesis will be that mu1, which is the population mean of this guy, right? Take away mu2 equals 0. And that's what salt does. It is equivalent mathematically to saying that. We agree? This is that. Any questions? Does that seem reasonable for the null hypothesis that the average iron content of both is the same? Now, in my story, I believe that there's evidence that the males have more iron in their blood than the females. Or equivalent to that, isn't that the same thing? This is kind of what salt would expect you to do. You know, in some of the questions they say, tell me the null and alternate, that's what you would type in, right? But that's the way I prefer. You might think, well, there's no difference. There is a little difference later on. We are only doing the first level. The first level is that the difference is 0. Later on, you can make that number 10, and you can do a hypothesis test. Is the difference bigger than 10? Right? In other words, not that I'm bigger than you, but I'm at least 10 more bigger than you, right? And so you can adjust that by this. You can't really adjust it if you use this notation. So that's why I prefer that. Even although we're never going to do anything except zeros, by getting you used to that, if you go on and do more statistics, you'll be able to say, oh yeah, we did it with zeros, now we'll do it with a 10. And so we collected data. And there's going to be quite a lot of data. Since I don't know what iron levels should be, this is made up. But for the males, it was 101. The standard deviation was 5. And I got that by looking at a sample of 151 males. So I got a random sample of 151 adult males and their iron level was 101, their standard deviation was 5, and that there was 150 of them. And then I did it with females, and they were 97, and their standard deviation was 10, and the sample that I used, just to be different, was 100. Superficially, does that look like I'm right, that men have a higher iron level than females? But couldn't that just be a random variation caused by randomness, right? You just get a little bit more males with more and a little bit less with women. Right? Just out of curiosity, is there any difference between iron levels in males and females? Because I know there's a difference in blood pressure. I believe males have a higher blood pressure than the same age group females. Is there any difference in the iron content?
I feel like females might have more iron.
Yeah. So that could be actually the total opposite of reality, but I'm just curious. Right, so what we want to do then is basically the same thing that we always want to do. Don't we want to test this as a hypothesis test, right, and get a p-value? So far, so good. So how do you do it? The good news is that pretty much it's all done through salt. And there are good reasons for you doing it through salt, because it would take you forever and a day if you had to do it all by hand. Just because you'd want to or don't want to, the standard error for the difference between two means is given by that guy. And that's the formula that you would use if the two samples were independent and had different and their standard deviations were not considered the same, right? In other words, different variances. If you made the assumption that the variances were the same, then this formula turns into an even uglier one, which I'm not going to write down. And that's not the answer. That's just one of the numbers you need to do to get the Z-score, which then becomes a p-value, right? So you can have I convinced you don't want to do it by hand, essentially, right? But if you're interested, you can actually look it up and actually see the numerical steps to do something. I'm about to hit salt, and we are going to check this out. So here goes. For most of you, if not all of you, this is the first time you'll actually have seen salt do a comparison one. But I think you should be able to do a good guesstimate of how it's going to be set up, even though you've never seen it before. Would you think a one sample, or which one of this list do you think we should be doing? One sample T, or who should we be using?
2.
2.
Would you agree that makes perfect sense, right? Now, that's going to be the one that we are going to do all the time. Now, there's another one down, well, there's lots of them down here, but there's another one called paired T. Do you see the paired T ones? Right. If you collect data on two populations, but they are definitely connected, I'll give you an example. One population had the husband and the other population had the wife, right? And, you know, John is married to Mary, right? They go together, right? Then in that question, what you would be doing would be taking the pair of data and subtracting them to make a single number. And when you do that, it's called a paired t-test. And what you'd be looking for, is there a difference, for instance, in the ages of a married couple, right? A male-female married couple, right? So you would take the male, take away the female, and you get a single number, right? If it was positive, that's because the guy is older. If it was negative, that would be because the guy is younger, right? And you'd average it out. And then you could do a test like, well, is the difference 0? In other words, on average, you marry somebody about the same age as you. useless piece of information, but I happen to know this. Do you know if you look at married couples, the age difference between the two is not 0? Do you know who tends to be the older of the pair?
Husband.
Yes. Do you know how many years roughly? On average?
7 years.
No, that's a lot, but I guess it's a good guess. 3 years. Right? So on average, and this is on average, so I guarantee you will have, your mum is older than your dad, right? I can guarantee you're going to get that. But on average, your dad will be older than your mum, and your dad will probably be around about 2, 3, 4 years older than your mum. And that is just, I guess, the idiosyncrasies of Western society. That's not true for each society. Some societies, that difference is a lot bigger, but that's their society, that's fine, whatever. So back to our 2 sample T. Now, sample 1 has already been described as the guys. So when you're reading the question, you have to make sure who's 1 and who's 2, because sometimes it's easy to get them back to front. So it's 101. There was 5, and that sample size was 150. And if you go to the second group, this was 97, 10, and 100. So far, so good. Guys' data, females' data. Our difference is always going to be 0 because that's the only stories we're going to deal with. But can you imagine in the future, it could be not only you're bigger, you're at least 10 years bigger, right? That kind of thing. You could put 10 in there if you wanted, but we're always going to be 0. And we're going to be, in this case, trying to prove that it's greater than, right? First guy bigger than second. Any gut feelings? Do you think that's going to be significant or not? Do you think that 4 years is a big enough difference to show up? No, really? I don't know. I love these questions. I don't know, because it's kind of, oh God, I didn't think it was that big. You know, well, that relative. Here we go.
The sample size is big, but it's not huge.
Right. The p-value is actually tiny. Do you see it? So wouldn't that be our classic, there's enough evidence at 0.5 level? I should have put that in, shouldn't I? I forgot to, but at 0.05 level. So it's statistically significant. Yes, men's iron levels are higher than women's. Based on the 2 data sets, 97 and 101, I don't think it's hugely different to be a problem. But of course, don't you want to know the difference between males and females? Because if you take a male's iron level and it's a certain number, and then you take a female's iron level and it's the same number, isn't the conclusions different? For a male, couldn't that be quite low? But for a woman, that's normal. You see what I mean? So medically, you know, if a woman's blood pressure is a certain number, couldn't it be quite normal for a guy to have that blood pressure, but a bit on the high side for a woman? You know, that kind of decision. So, you know, it's important to know these things. And that's basically the process. You like it? It has a lot of similarities. You just have 2 sets of data. And when you do your comparison, is the first guy different from the second? Is the first guy less than the second? Is the first guy more than the second? Are we good? Right, where am I off to now? Well, I should do my test just to finish it. So I forgot to tell you that this was going to be at the 0.05 significance level. So here goes. Our p-value, is it less than alpha? Is our 0.000156? Is it less than 0.05? And the answer is yes. And are we all happy about the 2 yes buttons that you press when it's a yes? what would that be? Statistic at the 0.05 level, we would reject the null hypothesis and the data statistically significant. Any questions? Right, so let me zoom over and do a version of this from WebAssign, and then I'll pick a couple of my own up, whatever time we've got left, maybe not a couple, maybe. So here's our story. A random sample of 49 measurements from one population, so I better write that down because I'll lose track of it, is 14. The standard deviation is 5. They then, how many was that? Was 40? Okay, so that was 49. And then in the other sample, which was 64, the mean was 17. And the standard deviation was 6. Test the claim that the population means are different. So I guess that guy is the biggie, right? Because you have to know I'm trying to prove it's bigger, less, or not equal to. Would you agree that's a not equal to one? Right. So when I hit salt, they probably will have all the data I want, fingers crossed, already, populated into the software. So I don't even need to type it. But, I get surprised a lot. And I just got surprised. It's not there. So we do have to put it in. And we're going to do 2 sample T. I'm glad I wrote all these numbers down. The mean is 14. The standard deviation of the first population was 5. And that the sample size was 49. And for the second group, it was 17. The standard deviation was 6. And in the second group, it was 64. And what happened there? It was 6. I've lost my keyboard. 6. I lost my keyboard. That is weird. Okay. I have a backup keyboard. Hold on a moment. I'm having technical difficulties here. Okay, I'm going to leave that guy and go back in again in case it was just some kind of glitch in the software. Weird. Has that ever happened to you in WebAssign that it just stopped? Wonder if my keyboard's... Oh, my keyboard has a battery in it. It's... I
I
think
was
my
gonna say
battery...
when my mouse died, it was because of the battery. It wasn't
Yeah.
working. So that might be
Yeah, I just got the mouse death warning.
Oh, yours is already... Yours is joining in sympathy with my keyboard. Right, all I need is this keyboard or the battery inside it to last the rest of today, right? And then I'll change it out. So we got it. That's 0, and we're trying to prove it's not equal to. Now, do you see this guy down here called assume equal variance? This is a pain in the butt because you get a slightly different answer to your p-value if you assume equal variance. Right? It's just calculated a little bit differently. And unless there's some explicit reason that they tell me, I assume that it's not equal, right? I don't see why I could make that assumption, right? But if they tell me it is, I'll use it. If I get the wrong answer, will you just go back and plug it in and get the right answer? Because that might be the only reason, right? I wish I had a better explanation. Technically speaking, I guess I could say, look, Are they too close enough to probably be equal? And so I'm actually going to break my rule. I'm going to assume they're equal, right? And I'm going to generate the results. And here is our p-value. Right, you got that number 0.0055? Now I'm going to say, assume they're not. Right, so 0.055, 0.045. Do you see it makes a difference? Right, 0.055 or 0.045. Is there anything in that story that assumes that they're equal variance? They told me nothing. So it's kind of guess, isn't it? Let me go through to the bit. If it was 0.004, then 0.004 would live where? I guess it doesn't. Does it matter? Assume equivariance. No. Okay, in this particular case, it won't matter because won't both of them be less than that number there? Right, okay. I wonder if they do that in case you picked the wrong one. Right, okay, I can live with that. Okay, and that's it. So I'm going to pick 0.0055. That's the one I've decided is the right answer. So, is the p-value less than the significance level alpha? Is 0.0044? Is that less than, what was the story using, 0.01? And won't that be a yes and you do the double yes story? So that is, we have evidence to prove that the first group is in fact different from the second. And I don't know if you saw that, so you didn't. Let me write it down. Is the p-value less than alpha? Is that number, that's the one I'm choosing to use, less than that guy? That's a definite yes, isn't it? So, yep, we can prove the 0.01 level. There's enough evidence to reject the null hypothesis, and so it's statistically significant. And then the second sentence would be, there's enough evidence to prove that the first population's mean is different than the second's. Are we good? Right, last one I'm going to do is make up my own story. So, what shall we pick? There is a duck in Scotland, right, called the Scottish duck, totally made up. And the Scottish duck in at least a sample that I got was £30. The standard deviation was 2, and that was with a sample of 100. So a £30 duck is probably like an ostrich, right? It's a big honking duck, right? And there is another population of ducks living in England that are closely related to them called the English duck. And the English duck weighs on average 28 pounds. The standard deviation is 12, and that this came from a sample of 200 ducks. And I want to prove, or see if I can prove it at least, is there enough evidence to show that Scottish ducks, right? Oh, I wrote it the wrong way around, are bigger, heavier than English ducks. And would you agree that there's a £2 difference? Would you agree that there's a huge difference in the variation of the weights of these ducks? So won't there be a lot of English ducks that are really fat and heavier than a lot of Scottish ducks? But we're talking about the mean, right? and decent sample sizes. So I have no idea whether this is going to work. So I'm going to put in a 0.05, right? A kind of middle of the road significance level to test it against. Would you agree that in this case, it would be a reasonable assumption that the variances are not the same? Right. Now, if this was 12 and this was, 12.2, I'd probably say, yeah, they're probably equal variance, right? So I'm just using these two numbers to decide whether I hit the equal variance box or not. In this case, I'm not going to do it. Would you agree they're different? They're quite different. So I'll set up the use salt button. Here we go. And let's see what kind of p-value we get out of this story. So you should be looking at salt. Yep. Okay. So it's going to be, as it always is, it's a 2 sample T. Scottish ducks weigh on average 30 pound with almost no variation, right? So they all weigh about 30 pound, give or take a very little. And that came from a huge sample of 100. The second group, 28. Standard deviation all over the place, but from a really good sample size of 200. I am not going to click the assume equal variance. We talked about why that's the case, right? The difference in the standard deviations is huge. And so I generate the result. And the p-value that we got was 0.023. So let's kick over to the whiteboard. And that was our p-value. And now we're going to do is the p-value less than significance level alpha. Is 0.023 less than 0.05? And the answer is yes. And so don't we do the do yes sentences? So I've shown that Scottish ducks on average are heavier than English ducks. Now, one change. Suppose, and this is what you should be doing when you do a hypothesis test, suppose at the start I decided that I wanted to use this significance level. If I did that, and I done the usual, is the p-value less than alpha, wouldn't the answer now be no?
I have a question.
Yes.
So in the problem up a little bit earlier, you say like the hypothesis was equals 0, and then the hypothesis 1 is greater than 0. How come
Yes.
at the bottom you do a p-value is less than the other one?
So if you want to test as mu1 less than mu2, is that what you're
Yeah.
asking there?
Yeah.
All you do is choose the less than symbol, and the p-value will come out just the way it would.
So
normally.
you just changed that one to less than to be what
Yeah.
the. Oh,
Yeah.
okay.
So yeah, you see the bit at the bottom where you have 0, and then you put greater than, less than, or not equal to.
Yeah.
Do you know the one? You just pick the less than, and the p-value will come out.
Okay.
So that makes you're hesitant. I'm not sure if I've answered.
I mean,
that question.
so like I know when you put it in salt, you pick like if it's less than, greater than, whatever. Are you picking that it's automatically greater than, or are you always picking less than for it to be?
The p-value, this bit here, the test,
Yeah.
is always less than, no matter what the story is.
Okay.
Right? Now, inside the story, there are 3 flavors, right? Depending on what the story is. So let me show you the 3 flavors. You could be trying to prove that it's greater than. You could be trying to prove that it's less than, or you could be trying to prove that it's not equal to. So that is when the greater than, less than, or not equal to part fits. That's where you get it, right? So in my case here, I should have been trying to prove it's greater than. So I'll generate my result. Well, my result changed a little bit because of that. So I picked the wrong menu, right? Wasn't I trying to prove it was greater than? So my p-value is still tiny. Now, a significance level of 0.5 or 0.05 worked, right? I managed to prove that Scottish ducks are heavier than English ducks when I used that. When I used this significance level, didn't we get the answer? No, it didn't work, right? I guess I should be putting in the real values, right? The p-value didn't change. It's just who I compared it against that's changing. Is there anything wrong with that? I mean, how can something that be statistically significant with one alpha, but then not be statistically significant with the other? And the answer is that there's nothing wrong with that. Doesn't it just depend where this is? So if you're unscrupulous, don't you find the p-value first and then you go back and figure out which alpha you wanted? And that is considered a no-no. You're not meant to do that. You're meant to live and die right at the beginning. Actually, before you even collected the data, you should have picked that number. And if it ends up being not significant, you have to be honest and just say, well, it's not significant, at least at this level.
Is there a level of like pseudo significance? Like say that you have an alpha of 0.01 and your study returns 0.01001.
Yeah, if you're being lawyer-esque, you fail. Not enough evidence. You hope that doesn't happen, but I can imagine it could. Yeah. One of the best things that you should always look at whenever you see a report is not always look at what the significance level is, although that's important, or that it was significant at all. They always tell you, or they should always tell you at the bottom, I'm just making up a number here, what the p-value is. And so you can go and look at that p-value and you should be able to see how significant among significance things is. How on earth does that work? I've got a doctor's appointment. Good. I don't know, pay those guys too much money, I think. Right, give you an example. I did 2 experiments on 2 totally different things, and both of them ended up being statistically significant at the 1% level. Would you agree that would make it on the 1% significance level? And we've actually seen things like that today. Would you agree that both of them are statistically significant? But isn't that one, for want of a better word, more significant? If you got a p-value like that, wouldn't you be quite pleased if you were a pharmaceutical company? Because wouldn't that be, take it to the bank, this pill is doing what I want it to do? You'd still be okay with that, right? That's legal, and you could say, quite truthfully, yeah, my new pill is better than the old pill. But in this case here, wouldn't you be able to say, heck yes, it's definitely better than it? You know, no argument. You couldn't squeeze it. Why is that important? Well, if you're using a significance level that's quite weak, you know, the 0.1 level, there's my first guy, right? There's my second guy. At the 0.1 level, isn't these are both statistically significant? They're both yeses. Wouldn't you be kind of hesitant on that one? Because technically speaking, isn't that a 9.1% chance that you got what you got just by randomness? And do you really want to risk someone's life on a 9.1% chance that you're wrong, right? That the new medication or whatever isn't really any better than the old one. On that case here, wouldn't you be really comfortable at any level, even although you only tested it against that? Do you see how the p-value tells you more information than that does? So that's our kind of thing for today. Last name, bye-bye. Oh God, no, not yet. Do last names, please. But don't leave quite yet. I want to show you something and then you can go. Okay, hopefully you're all done your attendance. And do a student view. Okay, got that. I'll be a few seconds more and then I'll be ready to show you what I wanted to show you. Come on, load up. Almost there. Right, I'm ready. Okay, so as you know, or should know, we're in week 6 and next Thursday is our final. So first thing I want to show you is in Canvas. Let's go into student view so it looks more like what you would see. There. There is a new file called Practice Final Exam with Solutions. So I've got a practice final so you get an idea of what it's like. And this is really not the WebAssign half, although some of these questions would be done using SOLVE. You know, like the stories I told you today, you would go to SOLVE to solve them, right? That kind of thing. But I'm showing you some examples of the types of things that you would be expected to do. So a whole load of multiple choice, which I kind of like. Maybe do it on a full page and then try and get out right there. So here are lots of questions covering kind of smattering of all the things that we've done. Here are the calculations that you would do for some of those stories by hand, just to show you how horrible they are. I did not do the double ones. They're ridiculously ugly. And so that's a resource for you. And the second thing I want to show you is that, are you now looking at Cengage WebAssign? Right. If you go there, you will notice that there is a lot of homework. We've already done this one. By tomorrow, we will have done this one. That's my goal. Then we're going to do this one. And then we're going to do this one. I'm not guaranteeing I'll get all of this done this week. I don't expect to. But if we do, that's great. If we don't, that's still okay. These two are due this Sunday. So this week is kind of a normal week, right? Sunday, get your homework assignments 7 done, get your online tests 7 done. It's next week things get a little bit hectic. We only really have 3 days, Monday, Tuesday, Wednesday of class, and Thursday is our final. And so you've got until Wednesday to get your last homework assignment 8 done, and online test 8 done. So what I have done is I've split the work into 2 guys due this Sunday and the other 2 guys due on Wednesday. But they're all here and visible with the exception of the test, right? Which will appear at the end of the week where it always does, right?